So in module 2, we are making inference about means of the population. That is module 2. Module 2 is means. Module 3 is about proportion. So we have talked about one population study. We use different formula for one population study. And then for two population comparison, we use different formula. And then for more than two population comparison, we use chi-square. So we have actually done examples for one population study, two population comparison, and then the third example, which I didn't have time to show you the answers. I plan to show it now. Okay. Okay, before I start with the examples answer, if you notice, whether you're doing for means, we're doing for proportion, whether you are doing for non-parametric test later on today, yeah, you always be following the same step. First, you state the hypothesis. The most important one is null hypothesis. Null hypothesis always says no difference. Null hypothesis is maintaining status quo. No difference between these two data sets. No difference. Yeah, it's always like that. If the question doesn't mention about the null hypothesis, you should be able to know that whenever we talk about null hypothesis, we are saying that between these two data sets, no difference. Okay, that is one thing you must always remember. All right, and then you need to figure out the calculated test statistics, and then the formula will be different for different kind of problem. And then you need to find the critical value. And finally, you compare the calculated value with the critical value, whether smaller than or greater than, it depends on the problem. And then you use that to accept or reject the null hypothesis. If you accept the null hypothesis, it shows that there's no difference. If you accept the null hypothesis, no difference. The goal is to reject the null hypothesis because you want to show that there are differences between the two data. Now, how is this useful? Let's say if you're doing research, you're collecting two data sets, and you want to see whether these two data sets are similar or not. Maybe in proportion, maybe in the means. Yeah, let's say means that whether the means of both are the same or not. If the means are the same, that means whatever experiment you do has no impact. Before and after, the population has the same means, so there's no impact on the means. So usually in experiment, you're hoping to show that the two sample, before and after, there are differences. So usually your goal is to reject the null hypothesis. Yeah. So you are learning a lot of this formula. Actually, nowadays you don't need to memorize them now, but you need to know when to use which one. Yeah, when to use which one. We have learned about z-test. Z-test is when the sample is when you are sure that the sample it has a normal distribution. Actually, the statisticians have been carrying out a lot of studies to document what does it mean by normal distribution. That's how they managed to come up with the Z table, the normal distribution table. So a lot of samples that we take in life, most of them will be having normal distribution. Most of them, yeah. So in the last lectures, discussion of the example, the first example is for one sample proportion. Yeah, one sample proportion. So in this problem, right, we are not looking at the means. We're not looking at the average number of survivors. We are looking at proportion. That means not means, not 50%. Yeah, not half of it. So here we in a sample, we find out that 60%, 60 survive, 60 out of 100 survive. And then we want to test whether this sample represent the population or not. You see, the population proportion is 0.5, but the sample proportion is 0.6, right? Because we take a sample of 100 passengers, 60 survive. You see, the number of passengers on the Titanic is not 100 people. It's more than that, right? But when we do sampling, we take less than that. So the sample shows 60 survive. So we want to know we want to know whether this 60% actually reflect the population proportion or not. Okay, with 5% significance level. Say 5% significance level means 100 minus 5. We are 95% confirmed. We're 95% confident that this will be correct. Out of 100 times, 95 times will be correct. Our guess will be 95 times correct. That's what significance level means. So, as usual, for one population, yeah, we are comparing the one sample with the normal distribution, yeah, with the population, yeah. So we will take the hypothesis that the proportion of the sample is similar to the population proportion. You see, hypothesis is always similar, no difference. So for one population, we'll be using this test statistics formula. So you just plug in, yeah, just plug in. You see, you must be careful. P hat is for the sample proportion. P0 is the proportion of the population. And then you just plug in the values and then you get the value 2. So this is the calculated value. Now, remember just now, we get the calculated value. So what? We need to compare it with the critical value. So how do we get critical value? For critical value, if it is a normal distribution, critical value can be acquired if we know the significance level. The significance level is 5%. Okay, the significance level is 5%. Now, because the null hypothesis says that the proportion is 0.5, similar, yeah, similar. Okay, then we'll be taking two-tail hypothesis. Yeah. So instead of taking 0.05% significance level, when it's two-tailed, we will divide the 5% by 2. We get 0.025. So we refer to the if you refer to the book, right? We will get the value of 1. Okay, so this is the e-book. So we want to find the critical value of a normal distribution. So given the significance of 5% divided by 2, so you get 0.025. Yeah, 0.005 divided by 2, you get 0.025. Okay, I just shared this is all right, a part of the book. Percentage points of the normal distribution. So the significance is here, starting from very small, all the way to 0.5. 0.5 means half, 50-50 lah. Your confidence maybe yes, maybe no. 50-50. You see, my mouse pointer, 50-50. So but then we for normal distribution, right? For most of the hypothesis testing, 5% is actually enough already. 95% confidence is actually enough. So 95% confidence means the significance value, the alpha value will be 100 minus 95. You don't look out for 95. You don't look out for 0.95. You look at 1 minus 0.95 because 95% is the confidence level. Is your confidence level. We want to find the significance. Significance 1 minus the confidence. So 1 minus 95%, right? So it's 0.05. Always 0.05. So you look at 0.05. You just go down. Okay, this column doesn't have because the bigger is 0.0023. Okay, this column 0.005, right? So here is 0.05. But wait, just now we were not looking for 0.05, right? We were looking at 0.025. Okay, 1.96. So there you go. You see, 1.96. Now, this is the critical value. Just now, the calculated value is 2, right? See my mouse pointer? So 2 is bigger than 1.96. So when 2 is bigger than 1.96, we reject the null hypothesis. Okay. So yeah. So that means there's no the proportion the proportion of 60%, yeah, is not the same as 5% of the population. The sample proportion is not the same as the population proportion. So in null hypothesis, we can only accept or reject the null hypothesis. That's all. It's very limited, but it can do a lot of wonders, because usually in experiment, we just want to show whether the idea is rejected or acceptable. And then example 2. Compare the survival proportions of males and females. So you see here, there are 2 samples of the males. We take 50 samples, and then 50 males, 20 of them survived, 30 died. Female, 50 passengers, 50 female passengers, 40 survived, 10 died. Now we want to see 20 out of 50, and the other one is 40 out of 50. Okay. Are these 2 proportions similar or not? I mean, of course, you can say that, okay, this is 20, this is 100, this is 40%. What for male is 40%, for female is 80%. Clearly not similar proportion. But wait, this is sample. We want to know at the population level whether the proportion is similar or different. So we want 95% confidence that the population, the proportion has no difference. So these are the formulas that you can use for two population comparison. Okay, so this is the answer. As usual, null hypothesis is that the both proportions are similar, no difference. Hypothesis is always like that, no difference. Okay, now because it's two population, so you see you'll be using different formula, right? First, you have to find out the full proportion. Yeah, you take the survivors, 10 from male, 40 from female, you total them out, and then you find the total. So the survival rate of all the passengers is 60% for the p hat. Now, then you are going to use the formula test statistics. Okay, actually I forget to put the formula for the test statistic here. Yeah, but the p hat here is used inside the test statistics. So you see, this formula is different from single population. So you must be aware whether it's single population or two population. All right. So, but this value p hat is important because we need to insert it. And then 0.4, 0.8. This one is actually from the 0.4 is actually from the male sample, male sample proportion. 0.8 is from the female sample proportion. And then 0.6 is calculated from the pool proportion. And then 50-50 is the total numbers of the male sample and the female sample. So if you do the max, you get negative 4.08. But we are not interested in the negative value. So eventually we take the absolute value of it. Now, again, you see, in null hypothesis, right, we are saying that proportion 1 and proportion 2 are equal, no difference. So wherever you see is equal, not greater than or less than, when you take the significance level, you must divide by half. So the 5% you must divide by half. That's why the z is not z over 0.5, 0.05, but 0.025. Yeah, it's always like that. If there's no difference, if you see the operator is equal, if greater than or less than, then you use a single tail alpha, which is 5%. But for a two-tail alpha, when is two-tail alpha? When the hypothesis says it's equal. When equal, you use two-tail alpha. Two-tail alpha means you must divide the 5% by 2 to get a 0.025. So why are we getting this? Because we want to refer to the standard normal distribution table. Remember, the first one, 4.08, is our calculated statistic. 4.0 is our calculated statistic. We want to find the critical value. Why is calculated value? We want to find the critical value because we want to compare the calculated value with the critical value. If the calculated value is greater than the critical value, we reject the null hypothesis. So you see 0.0025. Just now we have to look at the table, right? 0.0025 is 1.96. You see? So it's again it's the same value. So you just do the comparison. 4.08 is greater than 1.96. So we reject the null hypothesis. Example 3 is involving more than two populations, which therefore, using a different formula. We are using a chi-square formula. Just now we were using z-test formula, z-table formula, right? So chi-square is different. This is the formula given, and there are actually more steps to it. Chi-square is used when you notice that there are more than two populations. Here, we are comparing three classes of the passenger on the Titanic ship. First class passenger, second class passenger, and third class passenger. For each class, there is information on the total number of that class and the total survival. First class, 30 out of 50 survive. Second class, 60 out of 100 survive. And the third class, 90 out of 150 survive. Now, these are proportion, right? These are not means, these are proportion, fractions of survivals. So we want to know at the population level. These are sample, 50, 50, 50, 100, 150 here are sample. But we want to know at the population level, are these proportions similar or not similar? Similar or not similar? So we have to follow the following steps. First, we need to formulate the hypothesis. Yeah. So the null hypothesis is that population class, first class, second class, third class, the proportion has no differences. All proportions are similar. And then if it does not mention the significance level, usually we assume 0.05. That is the standard line, 0.05. Now, can you choose to use lower, 0.01? Yes, you can use 0.01. That is another common value. Or you can use 10%, 0.10. Now, this depends on your risk appetite. If you are risk averse, very risk averse, you take 0.01. If you are more to risk taking, you take 0.10. But if you are neither, you take the average of 0.05 as the alpha value or significance level, which means that you're 95% confident. 95% confident means out of 100 times, 95 times, your guess will be 95 times correct out of 100 times. Yeah. Now, if you're risk averse, you're scared, then you probably want to take alpha 0.01. Alpha 0.01 means out of 100 times, 99 times your guess is correct. Yeah. So for three population, the steps are different. You have to come up with the contingency table first. Yeah. So first, you turn this data into a contingency table. So on the first column, you state the population classes: class 1, class 2, class 3, and then the following columns will be used to show the number of survivors. Okay, and then we have the total, right? So we can come up with the number of deaths, non-survivor, by just taking the total minus the survived one. Yeah, 50 minus 30 get 20, so on and so forth lah. So once you get the contingency table, let's come up with the observed frequency matrix. Observed frequency matrix. So the observed frequency matrix is given as follows: the survivor. You see that three rows for the three classes, for the three population: the first class population, second class population, third class population. So on the left hand side is the survivor, on the right hand side the number of deaths. Left hand side survivors, right hand side deaths. So you just plug in from the contingency table that you have prepared. Yeah, 30, 60, 90, and then the non-survivor one is 20, 40, 60. So you see the first row is 30 survived, 20 dead. Second class or second row, 60 survived, 40 died. And the third class, 90 survived, 60 died. Okay, so that is the first part of calculating the frequencies. Then Then we need to move on to the expected frequencies. But before that, you need to calculate the proportion of survivors by using this formula. This formula is done by taking the survivors, you add them up, divided by the total. So you want to get the percentage of survival from all the population. So the value is 0.6, right? Okay, then we want to work out the expected frequency. Okay, just now we done the observed frequency, right? Now it's expected frequency. Now, this one is quite technical because you have to remember the techniques lah. It's technical. So the expected frequency is given by row total multiplied with the column total divided by the grand total. So how do you work out the matrix for the expected frequency? You see, just now the contingency table that we have produced is very important. Yeah, it's very important. So the first row of the matrix is first class, second row is the second class, third row is the third class, right? Not left-hand side survivor, right-hand side is non-survivor. But the formula to determine the value is different because you're using the expected frequency. Just now you are using observed frequency. So you take directly from the table. You don't do any manipulation. You take directly from table for observed frequency. But for the expected frequency, you won't take directly from the table, but you use this formula. So you see, instead of putting 30 for the first class survivor, right? You'll be using row total times column total divided by grand total. So how do we do that? You see, let's look at the first one, first class survivor. The survivor are 30 of them, right? But we're not taking this value. We're taking the row total. So the row total is what? The row total is 50. Okay, so we plug in 50. And then what about the column total? The column total go all the way to the bottom. You see, total 180. So you take 50 times 180 over the grand total. So where is the grand total? From the contingency table, the grand total of everybody is 300. So you divide by 300, you get 30. Okay, then you repeat with the second class. The second class survival 60, right? But this one you cannot plug in 60. That one is for observed frequency. Instead, we will take the row total, which is 100, multiply with the column total, which is 180, divide by the total passengers, 300. Total samples. Then you get 60. So you repeat for the rest. So eventually you get the value 30, 60, 90, 20, 40, 60. Now this is for the expected frequencies. So now we have the observed frequencies and the expected frequencies. So what do we do with that? You calculate the chi-square. So to calculate the chi-square, the formula given is you take the observed frequency minus the expected element, the observed element minus the expected element, square them, divide them by the expected frequency. Having calculated both the observed frequencies and expected frequencies, we move on to coming up with a chi-square test statistic. The result will be recorded in the chi-square matrix. So what we do is we must take the matrix of the observed frequencies and expected frequencies. They are of the same sizes, and by using the formula of chi-square, we will do the operations accordingly for each cell inside observed matrix and expected matrix. So for example, the first element, 30 in observed frequency and 30 in the expected frequency are subjected to the formula, resulting in 0. And then we repeat the same for the other elements in both observed frequency matrix and expected frequency matrix. 20 with 20, 60 with 60, 40 with 40, 90 with 90, 60 with 60. In the end, we will acquire the chi-square matrix, of which all the elements are zeros. And when we total up, all the elements inside, we will naturally acquire 0. Hence, the calculated chi-square is 0. Next, From this chi-square matrix, we reproduce the table. Earlier, we have the contingency table. Yeah. We will produce the chi-square contribution table based on the chi-square matrix. So here we have the different classes as the rows, and then for the columns we have the chi-square values of those who survived and those who did not survive. From here we can see that we have 3 rows of data and 2 columns of the chi-square values. That was for the calculated chi-square value. As usual, we need to determine the critical value from the table, from the statistical table. There is a page in the statistical table book for chi-square values, for the critical value of chi-square. Yeah. So how do we do that? First, we need to acquire the degree of freedom. The formula to determine the degree of freedom is rows minus 1 minus columns minus 1. So we'll be referring to the chi-square contribution table, which has 3 rows and 2 columns. So 3 minus 1, we get 2. 2 minus 1, we get 1. So multiply, eventually we get 2. So the degree of freedom is 2. Then we get our statistical book of tables, find the chi-square table, chi-square distribution table. You see, the critical values of chi-square. This is chi-square. Okay, so we want to find the critical value, the x square here, the chi-square here. So the degree of freedom just now was 2, and then 5%. You see, yeah. So take this one because 0.005. 5.991, we will acquire the value 5.991, which is the critical value of the chi-square. So what do we do next? Having the calculated chi-square value and the critical chi-square value, we compare them. Okay, so we compare calculated versus critical. If calculated is greater than critical, then we reject the null hypothesis. Since in our example, the calculated chi-square is 0, which is less than the critical value, 5.991. Thus, we fail to reject null hypothesis, because we can only reject the null hypothesis if the calculated value is greater than, but in this case, no, it's the opposite. Therefore, we fail to reject the null hypothesis. So as the conclusion, since we failed to reject the null hypothesis, we can say that at the 5% significance level, there's not enough evidence to conclude that the survival proportions across the 3 passenger classes, class 1, class 2, and class 3, are different. This suggests that class does not affect survival probability in this data set. Okay, I hope everyone is clear about example 3 solution now.